Welcome back, everyone. I'm so sorry I could not make the class today. I'm feeling okay. I just still have some sore throat, but I was really hoping I'll test negative today, but I didn't this morning. So I emailed you all as soon as I could. Uh, so we'll conduct this review online, and hopefully, I'll provide the as you know, I'm going to provide the recording, and hopefully we can address all your questions in the time that we have today, and then maybe I'll see where we are at the end of 11 o'clock when we get to 11 o'clock, and then if we still need some more time, we can use some lab time to go over some of the other things that we have left over. So what I did was in preparation for this review lecture, I did go over your muddiest point survey responses, and if you didn't respond, that's okay. You can still ask me questions and so forth. But I hope you also had a chance to look through the practice problem, which we can also go over, in the class or in the lab. But let me go ahead and share my screen and go to those muddiest point surveys so we can look at them together. So if you look at this one, so this was the one on the two fluid model parameter, and it looks like you all have pretty good grasp of how to estimate the two fluid model parameters. So you can do your homework problem pretty well. It's a very simple approach to do that, so that's good, because there is going to be a problem in the test related to this. So I'm glad that at least those who responded were able to grasp it, and if they represent the class, then we should be in good shape with that. And I was glad to see that you were able to also look at the driver aggressiveness in the two fluid model. Aggressive drivers can probably, when it's not very congested, they can decrease their free flow travel time, and then they can decrease their travel time, and that means they can have a lower value of TM, and then but their N value is typically higher, because as the congestion rises, they can't quite reduce their travel time by that much. So that's good. Now, this is something that the one where I saw a couple of threes there is define the relationship of the two fluid model parameters with operation on an arterial network. So when I say arterial network, I don't mean to say, I probably should have said maybe a better term for this would have been the surface street network. So we are talking about the downtown type network, downtown San Luis Obispo or wherever. We're not talking about freeways. We're not talking about uninterrupted flow facilities. We're talking about interrupted flow facilities like Broad Street and Marsh Street and Higuera and all of those places. So the relationship is that if the value of TM, so value of TM and N can define the quality of the network. So if the TM value is low, that means your travel time per mile is low under the theoretical free flow conditions. That means the initial speed at which the traffic flows would be high. So the TM is just a matter of if the initial speed is going to be high on the network. When I say initial, means without traffic, without a lot of traffic. If there is very few cars on the road, what's the theoretical maximum possible speed? And if that speed is higher, then TM will be lower, right? Because TM is just a reciprocal of speed. So that value would be lower. So that's what it means. TM value being low means you have you can almost say that you'll have lower. If TM value is low, that means you have a higher free flow speed, and if TM value is high, that means you have a lower free flow speed. Okay, so that's TM for you. N is a little bit more complicated. N value we know has to be higher than 0 because travel time does have to, as the stop time increases, the travel time does increase. But if N value is even higher, as N value increases, what it tells me is that the travel time rises faster than just the rate of the stop time increase would indicate. Okay, so here is I'm going to say it again. The higher value of N, small n, the two fluid model parameter N indicates, the higher value of N indicates that the total travel time, rises faster than just the rate of increase in the stop time. Okay, which makes sense, right? I mean, if n value is higher, that means your travel time is rising, not just based on the increase in the stop time, but also your run time is also becoming larger. So when you're moving, you're having to move slowly, even in that case. Okay, so that's the relationship with the arterial network operations. So you can define how lower or higher value of n and Tm correspond to what kind of operations you expect to see. So if n value is pretty high, you expect the operations to degrade way faster. Okay, you expect the operations of the arterial street to degrade way faster. So one could say that, yeah, maybe on an urban street, we want maybe a little bit higher value of Tm, so everybody's moving slowly when they're empty. So maybe you have some traffic calming measures in place, right? And then, but when you add traffic to it, the operation hopefully doesn't degrade very fast. So it'd be nice to have arterial streets that lead to, and then we've done some research on, like, what could lead to n values being higher and so forth, but that's not what I'm going after right now. That's not the point here. We're not trying to improve the operations on arterials at this point. We're just trying to understand how can we model and understand a surface street traffic flow, and n parameters, n and Tm, help us do that, the two fluid model parameters. And then definition wise, I saw a 3 there as well. So I would just point out, Tm is sort of the theoretical measure of the minimum, the travel time per mile, minimum travel time per mile, so sort of the maximum speed that you can achieve on your network. And n, you can say, is a measure of resilience of your network as to how fast do the operations degrade as you add more traffic to your arterial network. Okay, so that's basically the definition. Now, I will stop here, take a little pause, and ask you all, are there any questions? Maybe you didn't fill out the survey, or maybe you did fill out the survey and my explanations just didn't make sense to you at all. So I would love to hear that. Are there any questions? But in terms of the test, I think, yes, there might be some true-false type questions that you should be able to answer on n and Tm, but it looks like most of you got a good sense of how to estimate the two fluid model parameter. And I know I noticed some questions down below, so it's all about shockwave diagram. So we'll come to look at that in just a second. Okay, so we'll discuss all of those. They're all on the shockwave diagram, so we'll come and get to those very quickly as well. Okay, there are no questions on two fluid model. I'm going to move on quickly to the surrogate measure questions. So for the surrogate measures, I got 8 responses, which is good. So define surrogate measures, right? So surrogate measures are surrogate measures of safety. So surrogate is something that is replacing, that is something typically more complicated to measure. So crashes are not more complicated to measure. It's just that you have to have a lot of them to make any statistical inference about safety of a site, of a roadway location. So you need to collect a lot of data, 3 to 5 years worth of collision data per highway safety manual. And surrogate measures can do that sort of estimate of safety for you, can estimate safety for you with a smaller amount of, in a very small amount of time, by observing how close individual vehicles are getting as they're moving about in the network. Okay, so if they're getting too close, then maybe there is more crashes are likely to happen. More crashes are likely to happen, or crashes are more likely to happen. It's the same thing in some ways. Okay, now that's what surrogate measures are. Measures that we can use, traffic measures that we can use and measure over a smaller period of time to make estimates about safety other than the actual collision data. Okay, so it's basically they're surrogates for the collision data. So we're surrogating our measures like time to collisions, like post-encroachment time for collision data. Importance, what is the importance? You can make your inferences without having to have all the crashes occur. You can have, you don't need as much time. And then you can evaluate newer designs that don't yet exist in the field. So for example, there is no restricted crossing U-turns in California, but we could take a surrogate measures-based approach to assess how well they might work on rural expressway intersections in California. And that was your last lab was about, because we could simulate them in vSim. We could make sure that their travel time and everything was accurate. Thus, we can make some inferences about, you know, how to make sure that this is safety. Okay. Now, this was some questions where some of the few folks that talked about some ambiguity. So I want to go back and talk about this. Time to collisions and PET. So TTC is the time to collision. PET is the post-encroachment time. Okay. So let me go back and measure and talk about so I want to talk a little bit about the safety measures. Yeah. So I just wanted to quickly show you. So time to collision is established. Oops. So time to collision is established based on no change in the trajectory of either vehicle. Okay. So what we try to see is that we try to see if there was any change in any vehicle's trajectory in response to a collision or a potential collision. So we look for those things in the network. And if we observe any changes in the trajectory and we realize that was to avoid a collision, then what we do is, like, before that change starts, we project that trajectory as to what they would have done, what that vehicle would have done had they not applied the brake. So for example, this through vehicle, it's a time space diagram. So you know that the slope represents speed. So see, it's moving at a constant speed. And at this point, time T2, it says, okay, it looks like I might collide with this vehicle, right? That's approaching from the other side and approaching the same conflict point potentially. So I'm going to try to apply my brakes and slow down. So this vehicle slows down and basically delays their approach to the collision point or to the conflict point. Okay. To estimate the time of collision, we look at the trajectory before the through vehicle applies the brakes and project that original speed to the collision point. So remember, y-axis is the distance here. The y-axis represents the distance. So it's basically, it's the same exact point on the network. So this horizontal line represents the same point on the network. And if that vehicle kept going, it would have come this distance. So I'm going to draw it out here. It would have been this distance. This would have been the distance between the vehicle and between the two vehicles. If the vehicle continued in its path. So if this vehicle continued like this would have been, they would have come this close to colliding, because the time difference would have been between just T4 minus T3 would have been the time difference between the collision. So this is what we call the time to collision, is that this would have been, now if this value was smaller, even smaller, the through vehicles will probably be forced to brake even harder, because now they have even more chance of a collision. Okay, so that's what TTC is about. So TTC is based on a theoretical consideration of when they would have arrived had they not applied the brakes or not taken any evasive action. Post-encroachment time is a little bit different in that the post-encroachment time is based on the actual arrival at the conflict point. So if you look at this one, so I'm going to spotlight at here. So if you figure out the actual alignment at the conflict point, so you can see that the through vehicle actually applied the brakes. So slope changed, it slowed down. Now it arrived at conflict point over here. And if you take the difference between the crossing vehicle and the actual vehicle arrival time difference, this is your PET. So you could define your surrogate measures both as time to collisions, but also based on PET. And typically, PET would be larger. So we use larger thresholds for post-encroachment time. And what surrogate safety assessment model from the Federal Highway, they recommend TTC to be about 1.5 seconds, PET to be about 5 seconds. So anything less than that, you classify that as a surrogate event. So anytime there are more events with PET less than 5 seconds or TTC less than 1.5 seconds are happening, that means those locations may be vulnerable to more collisions. Okay, any questions about TTC and PET, please?
Yeah, I have a question about like the bottom curve where the vehicle begins decelerating. Is that, I'm just curious, is that like an assumed deceleration rate or what is it?
So actually, I'm glad you asked that, but because, see, this initial deceleration rate, sometimes and that doesn't, like surrogate safety assessment model doesn't do that. But a lot of time, in fact, we've also seen that initial deceleration rate can also be used as a surrogate measure. So yeah, we use like a specified deceleration rate. For example, in VSIM, we define a maximum possible deceleration rate that a driver could generate, right? Now we start to look for at which locations driver are having to decelerate at a rate that's close to that maximum level. Okay, and we can have a threshold on that, and that can also sometimes be used as a surrogate safety assessment measure. Okay, so yeah, so this is for now, we can use that, like we can define what that value would be, and then anytime that value goes below a certain threshold, we can say, hey, this is also a surrogate crash event. So yeah, for now, this is just an assumed value, but also you can think about using this also as a surrogate safety measure. For now, it's just an assumed value. It's the maximum possible deceleration that a vehicle would generate. Thank you for the question. Any other questions? Okay, good. So let's cross this out and go out of here. Okay, I'm going to go back and share the screen again. Okay, so we were talking about this. Role of trajectory data from VSIM. This is basically what your lab is about. So that was the next question. Trajectory data from VSIM gives you the information every 0.2 of a second. And then you can use that information to derive, using the surrogate safety assessment model, you can derive the, the trajectory data. I'm sorry, this was your lab, the previous lab. So remember how you can get the .trj files from VSIM, and then .trj files can be input into the SSAM. So that trajectory data basically gives you how close the vehicles are getting and so on and so forth. So the role of trajectory data from VSIM, you can take that trajectory data, .trj files, and feed that to surrogate safety assessment model. But the key thing here is that your model has to be very good. Your model has to be very well calibrated and validated for this to work. If your model is not well calibrated, then obviously if your travel time is not validated well, if your model is not showing you the appropriate travel time as it does in the real world context, if those two things don't match, if your VSIM model doesn't match the real world travel time condition, it's not going to be giving you good surrogate measures of safety. So it's very important that you validate your model first in a good way. You have sort of capturing the cues and the delays and all of that appropriately. But once that happens, yes, you can use your model and take the trajectory data and feed that to vSim to get your surrogate measures of safety. And then what we've seen is those numbers actually line up fairly well with long-term collision data trends, which is good news for us because building a model vSim is not a 3 to 5 years process. It's a process that takes time, but we don't have to wait for 3 to 5 years of crashes to happen. We can make safety determinations much sooner. Okay, so that's the role of the trajectory data. But the critical thing is having good validation in place. Okay, questions about this? Great. So what I'm going to do is I'm going to go next here. Okay, so we need to talk about the bottleneck stuff in a second. Okay, so it looks like you got the blockage length problem right. So basically there might be a very similar problem to your homework problem in the test. So hopefully that wouldn't be an issue for you all. It looks like write down equation for arrival rate, departure rate. So you got this right as well. That's good. Okay, so shockwave speed. So we are at the crux of the problem, and this is something that came up again and again, even in the even this was in the shockwave question, and then also when I asked for some additional inquiries, can you go over how to get the delay and Q length from the shockwave analysis, the practice problem for Q and shockwave speed, how to get the different points on the shockwave diagram. If you were not given a diagram to look at, that those are great questions. Yeah, so you can see that in the practice problem I did not actually give you the diagram. So I think our best bet, at least to me, it looks like, is to figure out, is basically do that practice problem that we did, and we can just go over that practice problem together here. And if there are questions, then we can try to sort of incorporate all of those questions into it, and then go from there. Does that sound good? And then hopefully that will help us sort of build on trying to get the questions answered and so forth. So I'm going to move on to shockwaves, but is there any other questions about surrogate safety, about any of this two fluid model or anything that else we've talked about in here that need to be answered for you before I just jump into the shockwave? Okay, yeah, so let's go to the main event. I think this is our key thing. Pause the recording for a second here. Okay, so first thing to remember is that shockwaves are just boundaries between two traffic regimes. So they will form anytime, and anytime there is a difference between flow rate and densities between two different traffic regimes. And typically that difference is generated either by a bottleneck. So anytime demand exceeds capacity, there will be a shockwave that would form. And those types of shockwaves are typically backward moving, forming shockwaves. So basically, as they're moving on the freeway, they move back, and they basically bring along congestion with them on the freeway segment. Okay. And I showed you that simulation, so you might want to check that out if you need a visual representation of that. Now, and why does recovery shockwave form? The recovery shockwaves will form when there is a congestion happening, but now the incoming demand is lower. When the lower incoming demand meets with a forming shockwave, then that might give rise to another shockwave that is actually leads to recovery. And that recovery shockwave would move with the traffic, and it would move with the traffic because the traffic as it arrives, the lower amount of traffic as it arrives and hits with that original shockwave, it's going to start to ease up traffic, and that easing of traffic would move in the direction where the traffic is also moving. Okay, so shockwave could be forming shockwave, there could be recovery shockwave. And by the way, there could be recovery shockwave moving backwards too, if the bottleneck is something that is temporary. If the bottleneck is something that's basically, is improving the situation, then that could be a good thing for us. Like, that could be that, we don't have to, that could improve situation as well. If the bottleneck is now improved, and like, for example, when the light turns green, think about this, right? When I want you to imagine a signal cycle. When the light turns red, what direction does the shock wave move? When the light turns red, that there is a traffic incoming, but now the traffic has to stop. What direction does the shock wave move when the light just turns red? You can answer via chat, yeah, or by unmuting yourself.
It moves away from the stoplight, right?
Yeah, away from the stop line. That means it moves backwards. So it'll have a negative speed. The shock wave would have a negative speed because it moves backwards, opposite the direction of traffic that you're looking at, right? So that's your shock wave, forming shock wave. Now think about, like, let's say now there is a queue in place because the light has been red for whatever 30 seconds or whatever it is. Now there is a queue. Now think about you're removing that bottleneck by turning the light green again. Now there is obviously going to be a recovery because now those vehicles are going to start moving again. But what does that recovery look like? What does that shock wave look like? It will be a backward moving, but recovery shock wave, because the first person in line would move first. They will leave, and then the next one will leave, and the next one will leave, and the next one will leave. And now there is a recovery happening, but that recovery also has sort of a backward motion. But because the intersections will hopefully have higher capacity flow, that will basically, catch up with the incoming flow, and there will be a sort of a complete recovery that would be happening. Okay, so shock waves are just boundaries between traffic, and they can move in either direction, and their speed is something that we determine using the formula that we have seen in the class, which is just this difference in flow rates divided by difference in densities. Yes, that's what you're looking for. So boundaries between two traffic regimes, you just look at the difference between flow rates divided by the difference in densities of those two traffic regimes, and that gives you your shock wave speed. So the formula itself is fairly simple. It's just that how we apply the formula that becomes complicated. Okay, so now let's look at that problem in the context.
Can I ask a question?
Please, yes.
So can you explain again why it would still be moving backwards if the light's green and the cars are then moving forward?
Why does the shock wave will be moving backwards, right? So why would still be shock wave will be moving backwards? Now think about this. When the light turns green, okay, the traffic will continue to come. So there might be a shock wave, that old shock wave will continue to form for a little while longer, right? Okay, so think about when the light is red, you have traffic still sort of, adding to the queue at the back, right? So there will be one shock wave that's still forming. Then when the light turns green, where does the congestion relieves first? At the top end of the queue or at the back end of the queue? At the front end of the queue or at the back end of the queue?
The front end.
The front end, right? So the traffic starts to improve at the front end first. Now, once the traffic starts to improve, now that has a new regime, right? The front end of the queue now has a new regime because now they have a lower density, they have a higher speed, they have a higher flow rate. Because remember, when the light is red, the flow rate is 0 in that regime. But now, as the traffic starts to move, the front of the queue has a lower density and a higher flow rate. Okay, lower density and a higher flow rate, right? So lower density and higher flow rate would basically give me a shock wave speed that's negative, right? So if you do the difference in flow rate and difference in densities, I'll get a negative number even for that recovery shock wave. Does that make sense?
Yeah, thank you.
Okay. So does that make sense to everybody? That was a great question, because I think about this, right? So when the recovery starts happening, where there is Q, Q is still there. It's jam density, maximum possible jam density, but and the flow rate is 0. But now at the front end, your flow rate is higher because you're now at least moving some vehicles, and your density itself is lower because now you have vehicles moving, so they're not as congested. So density is lower, flow is higher. So when you do the difference in flow rate and difference in densities for that front of the queue now, you'll get a negative speed. But that shock wave will have a negative speed, so it will still move backwards, okay? But it will be a recovery shock wave because actually it's easing congestion. It's basically making those vehicles move now. Okay, now we haven't seen that type of a shock wave in the problem that we did, right? Because our recovery, why did we not see that? Why did we not see a backward moving recovery shock wave? We never saw a backward moving recovery shock wave in our homework problem or in this type of problem. Why did we not see that? Because our recovery was always based on lower incoming flow. Our recovery was always caused by demand itself going down. Does that make sense to you all? That's why our recovery always started at the back end and then moved forward. So always our recovery shock waves were moving forward. Okay, I'll give you a minute to process that. And I would really appreciate if there are any questions. Okay, I'm hoping it all makes sense to you all. Okay, good. So now, going back to the problem. So it's very important that you understand what causes congestion, what relieves congestion. And depending upon what is relieving congestion, that sort of helps you determine where your recovery will start, of course, but then also which direction would the recovery move. If the recovery comes from removal of a bottleneck and restoring of the capacity at the front end, like we see on a signal turning green, then your recovery shock wave also move backwards. But on the other hand, if your recovery is caused by lower demand, like we've seen in all the problems that we have done in the class, in that scenario, our recovery starts at the back end and move forwards. So that shock wave will always have a positive speed because it will move with the direction of traffic. Okay, so now let's think about this problem. The demand is 3,600 vehicles per hour initially, okay? And then at t equal to 20, the demand reduces to 2,400 vehicles per hour. The capacity itself is 4,000, so that's good. However, at 10 kilometers downstream of the freeway entry point, there is a bottleneck due to a reduced shoulder width. So now the shoulder is reduced, the drivers were for whatever reason. So when you reduce shoulder width, usually the capacity of the freeway goes down. And this bottleneck capacity is only 3,200. There is also a ramp that adds 200 vehicles per hour at 3 kilometer point. Okay, so at 3 kilometer point, there is a ramp that adds in 200 vehicles per hour. If the free flow speed is 100 kilometers per hour, estimate the speeds of all the shock waves that will form, maximum Q length, using the shockwave method and the input-output method. So this is very similar to what you can expect to see in the test. I can even provide you with some more information in the test. I might, instead of maybe giving you these equations, I might give you the densities of different regimes directly. So be on the watch out for that. Even if you see the equations, don't just go ahead and start applying the equations, okay? Because I might give you the density values directly so that you have one less calculation to do. So just be careful as you're reviewing the problem, because these equations are only useful to estimate the densities of different regimes. So for example, first of all, would there be a queue? And where would that fall? Where would that queue fall? What is the X value? What is the location of the freeway where the queue will form? The queue will only form at 10 kilometers location, right? At the back, at the far end, at the downstream end of the network, because that's where the bottleneck resides. That's where the bottleneck is. Where the capacity is 3,200, okay? What is the total flow that's getting there that will cause the slowdown? What will be the demand value that you'll input at that? So for example, if you're thinking about the input-output method, what would be your flow rate or demand flow rate that arrives at that location? Can somebody give me the demand flow number? Can somebody give me the demand flow number?
Would it be 3,800?
3,800 is exactly right, because you have 3,600 from the initial point, 200 adding from the ramp. So total 3,800, and your capacity is only 3,200. Okay. So what you need to do is to be able to estimate the speed of the first shock wave, you just need to figure out, okay, if my congested regime, so I'll think about my congested regime and my uncongested regime. So for those two regimes, what I'm going to think about is, what is my flow rate and density? And then for uncongested regime, same thing. Okay, so that's what, I'm making it very simple now, thinking about, this is all I need to figure out. Do we know what is my uncongested regime flow rate and density are? What is my flow rate in the uncongested regime? What is the vehicle per hour that is passing through where there is no congestion? You can type it up in the chat. Nobody? What is my flow rate in the uncongested regime?
It would be 3,600.
Not 36 though, right? You have to account for the ramp flow as well. So my flow rate actually is 3,800. That makes sense? Because, so let's see. Yeah, so I see something in the chat that says 3,800, which is the right answer, because remember, the capacity of the main segment, the 10-kilometer segment, is actually 4,000. So as long as I'm below 4,000, no congestion. So my flow rate will be 3,800. And then I can easily derive the density, and this is per lane. This is the per lane flow density relationship. Okay. If this is my per lane relationship, then that's good, because then I can figure out, okay, that's fine. For uncongested condition, my per lane flow will be 1,900 vehicles per hour per lane, because it's a two-lane freeway. So my 1,900 per lane, VPH per lane. Density then would be, per this equation, Q equal to 100K, I can figure out the density. Okay, density will be 19 vehicles per kilometer per lane, or 3,838. So now I could figure out my flow rate and density will be 3,838. Does that make sense? Okay. Questions about this? Now for the congested regime, what is my flow rate? What is the flow rate when my traffic flow is congested at the bottleneck? How many vehicles can pass through the congested regime? I see something in the chat. 3,200 is exactly right. Does everybody see that? Why that would be the case? Because the congestion is because of the bottleneck, and bottleneck can only take in 3,200 vehicles per hour. Okay, so my bottleneck flow rate would be 3,200 VPH, and I'm going to figure out the density in a minute. That means 1,600 VPH per lane. My density would be what? Now, density is a little bit more complicated to get because I'll have to apply this equation right here. Okay. So if this is my density, I can figure that out by doing 1,600. So I'm just going to figure this out. Uh, 1,600 minus 2,500 is 900 divided by 25. Okay, so I just figured out this density will be 72 vehicle per mile or vehicle per kilometer total density. Okay, does this make sense to everybody? How I got to 72, or do we need explanation? Can somebody explain to me how the density would be 72 vehicle per kilometer? Yes, so I use the per lane relationship. That's exactly right. So when I use the per lane relationship, I actually got density was 36. So if you plug in 1,600 into this, so when you plug in 1,600 into this equation, you'll get density equal to 900 over 25, which is 36. So I'll say my density came out to be 36 vehicles per kilometer per lane. And then I double it because I have 2 lanes. So I get to 7,200 vehicles, 72 vehicles per kilometer. So this is another. Now I want you to use those 2 values to get me the shockwave speeds. Okay, now let's take a minute to estimate the shockwave speeds, please. I want you to do that. So the data that you're using, I'm going to highlight those in a second here. You're using these 2 data points, this one and this one. It doesn't matter which one you put first, which one you put last, as long as you're consistent. But all you need to do is difference in flow rate divided by the difference in densities. Does anybody have the shockwave speed for me? So I see an answer to be negative 17.65 kilometer per hour. Okay, negative 17.65 kilometers per hour. Is that what everybody got? Anybody got a different number? Any questions whatsoever about any of this? If you didn't get this number, please let me know. It's very important. And it looks like we are sort of getting to a point where we're running out of time. But before we leave, I just want to make sure that we understand this. And then we're going to meet at 12:10 also virtually on Zoom. And I want to wrap up this discussion, please. I want to finish up this problem. Okay, anybody got a different number or any questions about this? Okay, so we got 17.65 kilometers. So basically, this is the rate at which the congestion will be moving backwards, unless something changes, which it does at t equal to 20, where there is a new sort of, okay. Now, shockwave, as you know, when you draw the time-space diagram, shockwaves are just basically, they have a speed, units, they have speed units. So that's basically represents the slope of the line as it moves through the time-space diagram. So you have a line that has this slope, and then that same line also, we know that it passes through, because it takes 6 minutes to get to the 10-kilometer point at 100 kilometers an hour. So equation of the shockwave line, and you will need that, can be defined with slope equal to negative 17.65 over 60. And I divide that by 60 because remember, our usual axis of the time-space diagram will have minute on the x-axis, time axis, minutes, and then distance in kilometer on the y-axis. So we want to define that not kilometer per hour, but kilometers per minute. And that's why I'll have a slope here. And then one point on this line is 6 minutes to get there, get to 10-kilometer point, and then the 10 kilometers. So basically you have one point on the line that 6:10. The time value will be 6. The location value will be 10. And then this will be the slope of the line. And then we can use this line to come up with an equation for this shockwave. And then we can move forward with the next step. So I'm going to go ahead and so the question I was asked in the chat was that the shockwaves move sort of linearly, or is that an assumption? The shockwave, given that the assumptions that we're making about sort of, it's a good representation that they move linearly. Yes, so they do move in a constant speed for the most part, given that the assumptions that we make, other assumptions that we make about traffic, flow equal to speed times density, and then how speed and density are related, and things like that. So if you make all of those assumptions, they do move neatly. So that's a very good representation. So there might be obviously some non-constant movement in the speed, because you could have one driver that is not appropriately reacting, and so on and so forth. So maybe they're looking at something else. So maybe they create a larger gap between themselves, or some drivers are very aggressive, so they kind of move very closely. So there are turbulences that happen in the flow. But if you're trying to represent sort of an average state of the system, the linear assumption is a very good one. So no, they don't always move in a linear fashion, but linear assumption is a good way to measure it as we move, as we try to model this thing for a longer period. This would be very good, for the model. It gives fairly accurate representations of the delays and stuff like that. Okay, so I'm going to stop here right now. I'll see you back at 12:10 on the same Zoom room, and we'll pick up this discussion. Okay. All right. Thank you.